Hello, Mr. Collier here. Today we're going to tackle Kinematics Episode 5, Revenge of the Math, the Kinematic Equations. In this set of notes, we're going to talk a little bit more about the mathematical process of analyzing motion. So far we've talked about speed and distance, velocity and displacement, the difference between scalar and vector. We've looked at graphs and acceleration. And now we're going to dive into something that should be new for everybody, the kinematic equations. So far in this chapter, we've taken 5 different variables and use them to describe motion. They are displacement, time, initial velocity, final velocity, and acceleration. And now what we're going to do is look at all of these at the same time and use them to predict the future and explain the past, to describe motion in all the ways that we're going to need to. And really, all 5 of those values are locked up in these 2 equations that we've learned for velocity and acceleration. Here we've got time, displacement, velocity, acceleration, and within this we've got final and initial velocity. So those 5 variables are locked up in just these 2 equations. By using these 2 simple definitions, we're actually going to expand into 5 new equations by combining and substituting these, and these new equations are known as the kinematic equations. So what the kinematic equations allow us to do is look at those 5 variables in any combination and always be able to solve for all 5 of them as long as you have 3 of them. Now all of these equations rely on having a constant acceleration, and that's because this is an algebra-based course. If you want to do anything with a variable acceleration, you're going to need calculus, so we're going to stick to these algebraic kinematic equations. Let's take a look at the first kinematic equation. It relates delta x, initial velocity, final velocity, and time. So this equation does not contain acceleration. And if you have any 3 of these variables, you'll be able to solve for the 4th. Once you have those 4, you'll actually be able to solve for acceleration using another equation. The second kinematic acceleration relates final velocity, initial velocity, acceleration, and time. It does not contain displacement. The third contains displacement, initial velocity, time, acceleration, but does not contain final velocity. The 4th is just a slight variation on number 3. It swaps out final velocity for initial velocity, and a plus changes to a minus. But other than that, they're pretty much the same. And the 5th equation relates final velocity, initial velocity, acceleration, and displacement. Does not contain time. So notice that each equation has one thing that it does not contain. It has a main variable that it's solving for, and then it has the other variables. Each equation allows you to solve for one variable as long as you have 3, and then using those 4 you could always use a different equation to solve for the 5th. So any 3 things you know, you can find all 5 of these things. Make sure you get these 5 equations down onto your equation card. These are the tools you're going to need to solve a lot of the different problems coming up in class, and selecting the right equation is going to go a long way to being able to solve some of the problems we do. Real quick, I just wanted to show you how one of the equations is derived, and then if you're interested, I'm happy to show you all of them in class. So here's equation number 1, delta x equals 1/2 vf plus vi times t. And if we look at the definition of average speed, we've got 2 different ways we can define it, delta x over t, or we can just take the initial velocity plus the final velocity and then average it, right? There's 2 of them, divide it by 2. And if we set those 2 terms equal to each other, delta x over t equals vi plus vf over 2. Now if we just rearrange that equation, right, put the t on both sides, right, and then bring that 2 out front to make it a half, oh geez, that's the first kinematic equation. So like I said, you can derive any of the kinematic equations by using the definitions and then by rearranging and substituting different things into different equations. I'm happy to show you those if you're interested. So let's take a look at a sample problem. If a car starts at rest, what is the car's acceleration if it covers 20 meters in 2.5 seconds? So I know a starting speed, I know a time, and I know a distance. The problem here is that the equation for acceleration needs a final velocity the way it's written. So the equations I have already at my disposal won't allow me to solve this. I'm going to need a kinematic equation. The way that we're going to approach these kinematic problems, and really all of our problems this year, is by using something called the GUESS method. This stands for given, unknown, equation, substitute, and simplify or solve. You first need to identify what information is given in the problem, what unknown are they asking you to find, what equation allows you to relate those values. Then we simply put numbers into the equation, simplify it, solve it for the variable that we're looking for, and we get our final answer. So for our question, we're going to start with our given and our unknowns. So let's go through the 5 variables. It's a good idea to always start by setting up all the things you know and don't know. We know that the initial velocity is 0 because it starts from rest. The final velocity is not given to us, but it's also not being asked, so I just put a dash there. The acceleration is what we want to find, so that is the unknown. That's what we're trying to solve for. Time is 2.5 seconds, and delta x is 20 meters. From here, we need to pick an appropriate equation. That's what the E is for. So we need to look through the kinematic equations and choose the correct one. Really, the dash here can give us a shortcut to know which one to choose. We want the equation that does not involve final velocity, and that happens to be equation number 3. Delta x equals VIT plus 1/2 AT squared. Now we are ready to substitute into the equation. We're going to put all the values we know in where the variables are. So my delta x is 20 meters, my initial velocity is 0, my time is 2.5 seconds, my acceleration is unknown, and my time is again 2.5 seconds. Now you might notice something that's going to be nice here is when we have things where the initial velocity is 0, that term basically goes away because 0 times anything is 0. Now we're ready to simplify and solve. Reduce, cross-multiply, isolate the variable you're looking for, just work one step at a time. So there I've eliminated my term that was 0. Now I'm multiplying both sides by 2 to get rid of the half. And now I solve for A. When I'm done, I get my final answer. My units are meters per second squared, which is what I want for an acceleration. And I've solved my problem. One last thing, always box in your final answer or circle it so that it's easy to find on the page. Let's do one more example. How much room does a car need to stop going at 25 meters per second if its best deceleration is 2 meters per second squared? Again, we're going to set up our givens and our unknowns. We know the initial velocity is 25 meters per second. It wants to stop, so that's a final velocity of 0. We know that the acceleration is actually negative 2 meters per second squared. That's what deceleration means in this case. We know nothing about the time, and the distance, delta x, is what we want to find. So we're going to pick the equation that doesn't have time in it, and here that is. Now we're going to substitute our values in. We're going to solve for delta x. And we're going to round to the appropriate number of significant digits. From there, we might be asked the second question, how much time does it take for this car to stop? So now we have an extra piece of information. Now we know the delta x, and we don't know the time. From here, we could actually pick a couple of different equations, so you have a little bit more freedom once you have 4 variables. I'm going to choose the one that I like, substitute my values in, and solve for time. So hopefully now you feel like you have a decent idea of what the kinematic equations are and how you use them to solve problems.